Good afternoon. I'd like to welcome you all to our presentation. This presentation was created by the members of Team 86, Nita Kozadagi, Ethan Pardue, and Sean Hankins. Our model is intended to classify images taken from satellites into 21 different categories. This is useful for a wide range of applications, from surveying land to assisting in census data. We thought it was a very interesting and applicable project that would be a learning experience for all of us. Our model is roughly based on the NVIDIA course that covers the American Sign Language dataset. The NVIDIA model provided a great jumping off point for our team, seeing as the model's intentions of image classification were somewhat similar. A difference between our model is that our model has more channels on the input to incorporate RGB values to represent the colors of an image. The database we chose to use was the UC Merced land use dataset, which is a compilation of the most common distinguishing land features.
So this data set, UC Merced, it is a standardized data set of 21 different classes, and they each have even amounts of data per class. So this made splitting the classes evenly pretty easy and made us more confident in our data. As you could see in the code snippet on the right, we designed a convolutional neural network with 3 layers. Each layer uses a relay activation function, and they're followed by a max pooling layer to extract important features. After flooding and passing the output through a dense layer, which helps in learning high-level features, we added a dropout layer with a dropout rate of 0.2. And this means this layer randomly sets 20% of the input units to 0 during training, and the softmax activation function outputs a probability distribution over the classes. As you can see in this graph, there's a big discrepancy between the high training accuracy of 95.6 and the low validation accuracy that we have, which is only 28%. So this indicates that the model is overfitting. It's performing pretty well on the training data, but it fails to generalize to the unseen data. And Ethan is going to tell you about the plans that we have in order to improve this.
So our plan to improve the accuracy is address the issue. We have a couple of options for this problem. We can have our convolutional layers, which will be more competent in recognizing complex patterns and help discriminate classes and improve our generalization performance. We could also try to use batch normalization as the model. Maybe try different batch sizes, especially one by improving accuracy. And finally, we can increase the number of blocks to help be more mindful of the possibility of overfitting. But to show you the improvements that we made in our model, we saw a slight increase in validation accuracy, but still a very high training accuracy, which really just cemented the idea that overfitting was the issue that we were having. And we believe it is still indicative of improvements. So, like we were just saying, a potential problem could be overfitting, but it could also be with our small data set, because even though we have 21 classes and 2,100 images, there's only about 100 images per class. So we're going to attempt to use dropout layers and data augmentation methods to but we think that it would be smart to incorporate other strategies such as fold cross validation and potentially trying to create new types of data so that it can generalize more robustly. And lastly, we think that there might be a problem between class ambiguity, meaning that some of the classes are so similar that it's difficult for the model to recognize a difference between them. So for instance, we have this forest and river class, and side by side, you can see that they're pretty similar, and we're going to take some steps to address this problem as well. And lastly, I'd like to thank everyone in the class who was us, from Professor Lobaton to the TAs and our peers that have all been very helpful in creating a very interesting experience. Thank you.